we're going to talk about how it is that we go from the number of operations Fn to one of the complexity classes that we discussed earlier. So if we talk about this, right, these are basically simplified expressions of the number of operations that we need to deal with when we analyze an algorithm. So it's just that for most cases, your number of operations is not going to neatly fall into one of these cases simply. So in that case, then we need to somehow or another categorize them in this form. So we're going to do that through what we call asymptotic analysis. Now in there, the subtitle says measuring performance in the limit. I would explain this in a minute, and I think it'll become clearer a little bit later. Okay, so we're going to introduce what we call a big O notation. And in a big O notation, what we are attempting to do is to simplify the number of operations Fn, right? So we started out with Fn, which is a number of operations you expect to have for a given input size n. And we are attempting to arrive at another function gn, and gn usually is a simpler form. So which means that it might be one of the complexity classes that we saw earlier. And the concept of the big O is that of upper bound, which means that given the number of operations Fn, I would like to be able to characterize what is the upper bound to Fn. And the intention of doing that is so that I can tell what is going to be the rate at which Fn grows in the worst case. It means if I estimate its upper bound. Now let's assume that your Fn, you plot your Fn, right? So given an input size, so your input size here is n. So here you have an increasing n, and you're going to input the Fn in terms of the number of operations you need to do. Now, Fn itself, it might fluctuate over time. That means that it may start out high, it may go down, and so on. Now, but in any case, what we are interested in is the portion of Fn when the n is large. So that means that we are really looking at the cases where n is large. And the way that we express that is by saying that we are concerned about this analysis, but we're only going to be concerned with n of a specified minimum value. And the minimum value is something we call n naught. Okay, so n naught is, okay, or n0, right? And this is a threshold value, which means that below that input size, I'm not going to worry about it. But above that input size, I'm going to care. And as the n grows, we are going to characterize the shape of the function Fn. And because Fn itself is a complex function, so we're going to try to express it in terms of a simpler function gn. And the way that we are going to claim the big O is by forming the following inequality that has to hold true. So which means that my function Fn has to be lower than the function g of n multiplied by a constant c for any n value greater than the constant n naught. So which means that to be able to say that Fn is O g of n, to say this statement, I need to be able to identify a c and an n naught such that this statement is going to be true. Okay, now this c can be any c, the n naught can be anything, but the point here is that by the time we come to the following expression, it basically says that my Fn eventually is going to grow roughly at the same rate as Gn when n is large enough. So I repeat, okay, so when n is growing large enough, my Fn is going to grow roughly at the same rate as Gn. Now the constant g doesn't affect my growth rate. So it means that if my n doubles and so on, right, it's going to affect the Gn. But the constant c doesn't affect my growth rate. And therefore, I don't really care about the c. I would just say that Fn is O g of n. Okay. Now let's say, for example, okay, let's take a look at a few examples. Okay, and because of this big O, it turns out that we can do certain simplifications. We can drop constants. Now let's say we have an Fn that is for n, right? Now this for n, I can write it as Fn less than C of Gn. And what is Gn? This Gn here, for example, could be just n, right, which is given here. Now I just need to find a C where this is always true. Now for n less than C of n, so I can find such a C to handle that. For example, I can just say C equals to 5, right? Now if C is equals to 5, then this inequality is always correct. Now, okay, but n can be negative. But n stands for the input size. So the input size is not negative. It's usually some non-negative number, 0 and above, right? So in that case now, having found the C and having specified the n naught, then we can write the Fn is On. Which means that when I'm describing the complexity of this class, I can actually ignore this constant. So we call the coefficient that precedes the function of n, right? The n value there is basically some constant. Now, you can have a bit more complicated function. So instead of a constant in the multiplier, you can also have a constant in the addition. So I have a function that is Fn plus 2, right? Now, for n plus 2, right? Well, is it always less than 5n? But if my n is 1, for example, then 4n plus 2 is a 6. 5n is 5, right? So 6 is not less than 5. Well, that's fine, because we can still play with the n naught. Well, in that case, I will specify 4n plus 2 is always less than 5n for n greater than or equal to 1. So which means that, even that is not enough, right? So I need to specify 2, right? So I can say that my n naught now is 2, my C is 5, and therefore, in this case, for any n greater than 2, I can write 4n plus 2 is less than 5n. Now, which means that what is the Fn here? I can write it still as On. Okay, so now based on these rules, we can always drop constants. So basically, the constants either is a multiplier constant or an additive constant. In both cases, we can drop it. Now, then we have the following, right? So you may have more than one term. So in some case, you have n squared plus n log n. Now, so in this case, n squared plus n log n, you're trying to describe it in terms of n squared, for instance. So we have n squared plus n log n, right? And this is less than n squared. Well, n squared here is the same, right? But I can multiply it by c, right? So which means they're going to have 2n squared. Now, this is correct because the n squared and n squared here is equal, but the n log n is less than n squared. Now, because I have found a C that allows me to do this, then I can do this for On squared. Now, you can more or less infer that when you have multiple components, you just need to concentrate on the one that is the most dominant one, which means it's going to be the largest value. And what is the reason why we do that? Well, we focus on the largest value because anything that is smaller, we can always express it in terms of something that is smaller than the dominant form. And especially given the notation that what we are concerned about is n greater than n naught. Now, this allows us to bring the n to some arbitrarily large sizes where the dominant term is really going to dominate. So let's take a look at an example, right? Okay, let's take a look at the Excel. Let's say this is in this case n squared and n log n, right? Okay, so let's say this is n, this is n squared, and this is n log n. So let's say we are going to, increase this, let's say to in the logs. Oh, that's okay. Maybe I will just use a simple form. Like by 10, and I probably don't have to go very far. Okay, so what is n squared? Well, n squared, I'm just going to take the power of this to 2. And what is n log n? Well, this is going to be this multiplied by the log of this number, right? So now let's see what's going to happen, right? Now in this case, I have the following growth versus the following growth. Now then I have the sum of the two, right? So initially I have n squared plus n log n, right? And if I take the sum which means that this is the final number that I'm getting. Right now, the question then we are asking is that, well, how is this number related to each of the two components? Well, it turns out that if I'm looking at the proportion of the dominant term within the sum, right? So if I take the fraction, and what I'm doing is that I'm taking the fraction of the b over the d, right? Which means that I'm looking at how much contribution does the dominant term provide to the whole sum. And we call it dominant for one reason, because effectively the contribution is close to 1. And this is especially true if the n is large. So which means that if you have a threshold that is going to be high enough, then the dominant term would always dominate. If that is the case, then the only growth that you care about is a growth in the dominant term. You don't really care about the growth in less dominant terms. And for that reason, you can more or less drop them from the big O. Then you get a simpler form that tells you about how this function is going to be growing. Okay, so for the big O, one more case is that of the polynomial. Now, when you have a polynomial form, you can just keep the highest degree. And even so, you can drop the coefficient. So in this case, you have fn equals to a0, and so on until ad to nd, right? Now, in this case, the coefficients, the a's, they can either be positive or negative. So in that case, we can actually bound this. So the function fn can be bounded if we just take every coefficient and put it to be the absolute value. So this absolute value means that if it is negative, it's going to be turned into positive. And because of that, it will form an upper bound because n is always positive. So n raised to any other power is always going to. So now, in turn, because n is positive, it means that the higher the power, the higher the n, right? So in that case, then we can write the last line here, right? Which is that I can pretend that every power here is basically the same as the highest power. And in that way, we have found a constant c and a threshold n naught, such that we can show that fn is O and D. Okay. Now, because it's an upper bound concept, which means that the big O, whatever function you put inside the O, is kind of an upper bound to your original fn. So that means that technically you can specify any arbitrarily complex function to do so. So for example, you say fn is n squared, right? So which means that fn is O n squared. So in this case, n squared is also less than n cubed, right? N cubed is also less than n4, and so on. So can we now say that a function that is n squared is O n4? Well, technically we can, because it meets the definition. But even if it meets the definition, it's not very useful because it's presuming that it's growing much faster than it really does. So it means that we don't really want to do so. Instead, we try to be as tight as possible. So the best answer then will be n squared. So for this reason, in tests and exams and so on, if you ask you to get a big O and you overestimate it, and there is a simpler one, we usually penalize it. Because we want you to build a habit that when you talk about a big O, beyond meeting the definition, you basically want to make sure that it's actually useful. And the useful case is that if you can estimate the growth rate to be as close as possible to the actual function. Okay. All right. So I'm going to give you a couple of working examples. But before that, let me just describe two more notations. The notation here is that there is a notation of omega, which is kind of a big O, but it's the opposite. It's a lower bound now. So lower bound meaning that we can show that Fn can always be higher than Gn, right? But in this case, actually, Quanchen reminds me there should be a C here, which is correct, yeah. In this case, we are going to say that Fn is omega Gn, which means that Gn is a lower bound. It would be growing at least this much. Okay, so in some cases it may grow higher, but it must be growing at least this much. Now that brings us to the last thing, which is theta. Theta means, in this case, a tight bound. You bound it below, you bound it above. So which means that we can express the function fn to be between c prime of gn and c double prime of gn again, right? So which means that fn more or less grows at the rate of gn. Now, to be able to say this, this is a good thing, because in that case you have found a function gn that is pretty characteristics of the fn itself. Now, in most discussions, we stick to big O, because most of the time we are still most interested in the worst case, like what is going to be the upper bound of the running time, and therefore we talk about big O. But it's useful to know this big omega and big theta, because they still mention it in different reference books. So depending on what is the property that you're trying to establish with regards to the algorithm, you might find it useful to know what is this big omega and big theta. Okay, so now related to the previous concept of why in the limit, well, this is kind of explained by the threshold n naught, right? So we say that we're interested in n, but we're interested only in large sizes of n. Why? Because in the small sizes of n, right, all these numbers don't mean very much. They don't cause much differences. You're talking about 100 milliseconds here to 100 milliseconds there. So they don't matter much. But in the large sizes of n, then suddenly you see a difference between 9 and something to the power 154. That is going to cause a very drastic difference in the running time for these algorithms, and therefore you need to take care of these cases. Okay. All right, so now how worthwhile is an efficient algorithm? Well, in a way, if you think of your algorithm as being part of an engine, right? So think of it as you have a factory and you want to apply your algorithm to solve a particular problem to produce a certain throughput in terms of the output. So then what you care about is that what is the size of the problem that you can solve. If the algorithm can solve big problems, it means it's a powerful engine. If the algorithm can solve only simple problems, it's not that powerful. Now, it turns out that, let's say if you make that kind of a measurement and you say that, okay, so let's say I have 3 algorithms, and let's call it f1 of n, f2 of n, f3 of n, which means that these 3 different algorithms have different running times. Now, if the running time is 400n to n squared to the n, and let's say assume that each operation is going to take me like a microsecond, so which means that within 1 second, with the first algorithm, I can solve a problem of size 2500. In 1 hour, I can solve a problem of size 9 million. So I can, solve much bigger problems. But if my algorithm has a complexity of 2 to the n, which is exponential, so I can go in 1 second 19 to 1 hour 31. Now, even if you go to 24 hours, you're not going to get much more than that. So which means that having a more efficient algorithm is like buying a more powerful machine. Now, in some cases, in fact, it's more worth it than buying a powerful machine. Because let's say if you take the exactly same algorithms and you buy a new computer that is 256 times faster. Now, 256 times faster is like having 256 computers, right? Let's say you can parallelize the operation, assuming. Now, but even so, if your runtime is linear, so then the new maximum problem size that you can do is going to be 256 times before. So it means that you can make use of every single new machine or every single new power that you have to solve a much bigger problem. But if you have a runtime that is 2 to the n, and even if your computer is 256 times faster, in the end, you can only solve a problem plus 8, which means that the size of the problem that you're solving is actually still smaller. Now, having a good algorithm, not only is it worth the power of a good machine, more than that, it makes better use of your computers. So which means that even if you buy at 256 times, if you're an efficient algorithm, the hardware that is better is going to be a multiplier to the power of your algorithm, and vice versa. So which means that that's why you try as much as you can to optimize the efficiency of your algorithm, because the more optimal it is in terms of the runtime, the better it is in terms of the power that you can give in terms of solving your problems. Okay. All right, so let me just go through a few simple examples, and then after that, we're going to do a few in-class exercises. Okay.